Hi, everyone. In this version of the Women in Data Science workshop, I'm going to be presenting some of the insights that I've learned implementing machine learning solutions in the real world. My name is Rachita Naik, and I'm an ML engineer at Lyft. So, let me go ahead and briefly introduce myself before getting into the workshop. I've been working at Lyft for the past 2 years, and previously I completed my undergraduate studies in computer science from India, and then went on to pursue a master's degree in computer science with a focus on machine learning from Columbia University. During my grad program, I interned as an ML engineer at Lyft, and that's when I decided I wanted to pursue this full time as well. So I rejoined Lyft, have been working there for 2 years now, and I'm very passionate about creating impactful software solutions that harness the power of AI to address real world challenges, especially to make rideshare smoother. So, looking back, there were a couple of instances during my formative undergraduate years, as well as during my more recent Lyft internship, which cemented my decision to pursue a career in the field. During my undergraduate years, I worked on developing deep learning models for diabetic retinopathy detection and breast cancer classification and treatment planning. This was pretty impactful since it was deployed in local hospitals in Karnataka in India, and it currently aids the diagnosis of several hundreds of patients annually. So I've linked the papers in case y'all are interested in reading further, but that basically revealed the transformative power of AI in healthcare when deployed on a large scale. During my more recent Lyft internship, I developed an end to end training pipeline using a gradient boosting tree model to predict the probability of a ride being served by a cost efficient driver. And that was integrated downstream into the rider pricing algorithm. And it's currently impacting millions of rides. So that was my first transition from an academic setting to a production environment, and all the challenges that came with dealing with production world data. So it was a pretty defining moment in my career as well. Before I delve into the technical content, in this section, I wanted to cover some of the insights that I gained while completing my graduate degree as well as during my job search phase, which I think might definitely be helpful for someone in a similar situation. So it's definitely not an easy grind, but I think with the right mindset and prep, you can definitely be in control of things that come your way as you build a strong foundation and start your career. The first and foremost, I would advise to anyone pursuing a graduate degree would be to try to cover as much breadth as possible in the first and second semester, because that's the time you can really explore all the courses that excite you, and also try to have a good combination of theory and application as far as possible. So that helps you build a strong foundation in the field. Some of the courses that I took during my grad program were the machine learning basics course, which was math heavy, and it covered fundamental ML algorithms like Bayes theorem, classification and regression techniques, decision trees. The practical deep learning course was more assignment focused. So you could actually implement some of the deep learning techniques that you learned about. This involved neural networks, regularization, hyperparameter optimization. One of my most favorite courses was the cloud computing course because it had a strong focus on building end to end applications using AWS and GCP. And that's as close as it gets to actually building production grade applications in the real world. So it's really helpful for system design learning. Another tip is to always try to dig deep into the technical details as far as possible. So, whenever you're learning about these algorithms, try to read the technical papers for these algorithms and like dig into the data sets, the implementation techniques, and approach professors with any questions that you might have. Another way to really understand these algorithms is to implement mini projects leveraging some of these concepts, either through Kaggle datasets or by joining a research group under a professor who's working in your field of interest. One common thing that grad students often overlook is planning ahead in advance and planning your semesters wisely. You have a set number of credits that you need to fulfill for a grad program, and a graduate degree is definitely quite short and quite overwhelming. So you would want to plan the courses that you want to take in each sem. The courses offered, some of them are super popular, so they fill out easy. So you need to be aware of course deadlines and balance your workload along with other activities like internship search, job prep, etc. Another critical skill during grad school is networking, because the alumni network of each university is generally quite strong, and seniors are more than happy to help out with respect to identifying best courses or picking the right course schedule, job search, and internship opportunities. Coming to job search, this can definitely be quite challenging because, especially in the current environment with several layoffs, but the idea is to always start early. The ideal goal for your grad program should be to try to secure an internship for your preferred role in the field, because this will provide you with some experience in sending out applications, building resumes, and interviewing. And if you end up with the company that you actually want to work for, then you can also get a taste of the company's culture and the nature of your work. So you get a sense of how this will look like if you decide to pursue it full time. Mock interviews are also super helpful. So universities conduct several mock interview rounds with alums from various companies. So definitely look out for those and seek help from your peers as well, because this mimics the actual interview, so it can be super helpful during preparation. Attend career fairs and always be succinct with your introduction, and follow up on LinkedIn, because any of these opportunities could actually end up being full-time employments. So definitely network on LinkedIn as well. I've linked some of the GitHub job opening databases, which I found very helpful while doing my job search, because this is like a centralized repository with all the openings, especially for entry level or internship roles. So definitely look into those if you're in the same phase. And I've linked a couple of tracker templates, which I use to be more disciplined and methodical to track my applications during my job search. Getting into the details of an actual ML interview pipeline, I've listed some of the steps, especially for an entry level. So they generally have these following rounds, but it could vary depending on the company. But the first round for any interview is usually a resume deep dive, where they delve into the details of your past projects, your experience, and if you've completed any ML or deep learning projects in the past. This can be helpful because you can delve into the technical details of the algorithms that you've implemented, and address any architectural novelty in your solution. And this generally casts a positive impression early on in the interview. The second round is the technical phone screen, which is a coding round. This includes regular lead code questions of medium to hard levels, and it could also have some questions around implementing simple ML algorithms like KNN or K means clustering. So make sure you know the pseudocode for those algorithms as well. The next round is an ML conceptual round. So this questions concepts based on specific scenarios which are actually faced while building machine learning models in production. So questions like what would you do if your performance on the if the model performance on the test set is poorer than that observed while training, or what are the specific metrics that you want to use for evaluating your model when you have imbalanced data, or when a false positive is costlier than a false negative. So try to look through some of these questions online, because these can help during such rounds. The offsite generally consists of an ML system design accompanied by more rounds of coding. In the ML system design, I like to walk through these steps, which I've listed below, while I'm talking through the solution. So, if once they provide a problem statement, assuming there's a question like predicting the number of rides on a Saturday. Suppose I'm interviewing with Lyft, and there's a question like that, then you would want to ask clarifying questions to understand the product requirements and constraints. So if you need to build a model to predict the number of ride requests on a Saturday, you would want to know if you have historical data available, particularly signals like how many drivers have been driving in the area during the past few Saturdays. How is this data stored? So these questions can help you understand the constraints, because that limits the solutions that you can build forward. The next step would be to identify evaluation metrics and set up your training pipeline. So, talking through techniques like cross validation, hyperparameter optimization, these are all very commonly used in ML production pipelines. And you would want to include that in your solution as well. Once you've designed a high level system, you would want to talk through tips to scale the system, because that's generally a very important component in production systems as well. Oftentimes, one of these rounds are replaced by a take-home project, which involves implementing a prototype solution offline and then presenting it during the offsite interview. And there they can ask you follow-up questions around the solution. The last tip I'd say is to always research the company's products, their strategy, culture, and direction with respect to AI and ML to understand your future growth potential in the company. I'll ask questions and brainstorm about the potential use cases of AI that could be leveraged in their company, and discuss the risks and trade offs of implementing these solutions, what the data could look like for their training pipeline, because these are very relevant questions for production grade ML problems. And it also portrays that you have a more holistic approach towards problem solving. So, for the rest of the workshop, I'll be talking through the technical details around the individual steps in the ML training pipeline and some of the challenges that I've faced while implementing this, as well as the corresponding solutions. Before I get into the training pipeline itself, I wanted to talk through some of the AI and ML use cases, specifically in rideshare, since it's not really widely discussed from a technical perspective. The most critical use case of AI in rideshare is the ETA prediction, which is the estimated time of arrival. This is the pickup time estimate in which the driver is going to arrive to pick you up. And on the back end, multiple routing algorithms need to analyze historical data, traffic conditions, weather, and other real time features to predict this critical estimate. Since it also needs to adapt to disruptions, this can be either long term. For example, during COVID 19, we had several pandemic induced changes in commuting patterns, or short term road closures, traffic jams, accidents, etc. Given the dynamic nature of rideshare, it's also necessary to leverage this real time data to adapt to these closures, accidents, and suggest optimal routes to drivers, because we don't want them driving too long to either pick up or drop off passengers. A critical use case of AI in rideshare is the dynamic pricing and demand prediction problem. To put things into perspective, I can provide an example. So, suppose there's a Taylor Swift concert and the concert ends. There's a sudden surge in demand in a certain location at a certain point in time. At this instant, you want the algorithms to predict fares and adjust fares in real time, because there are not enough drivers in the neighborhood to fulfill this sort of demand. So, in this case, you would also want to predict demand ahead of time, because you would want to determine driver incentives and optimally deploy drivers so that they are in the right locations at the right time. AI has also been used to detect safety issues and enhance security while using the ride sharing platforms. This involves flagging ride deviations from expected paths and implementing AI powered verification for passengers and drivers. We've also been working towards personalizing user experience while using the app. So, this involves suggesting likely destinations when the rider opens the screen to request a ride. This would be based on past user behavior, or if they're in a new location, it could also suggest the most popular destination requested by most riders in the area. A recent use case of AI is the NLP based agent for customer support. This automates the alleviation of several commonly asked issues and frequently asked questions, and reduces the manual intervention. So, the time required to actually fulfill these concerns is quite short. Transitioning from academia to industry, I had several steep learning curves since nothing prepares you for the real world production applications that you deal with in the industry. So I'd like to talk through some of the steep learning curves that I faced. Initially, I had to in the first few months I had to onboard onto a new technical stack because a lot of our services use Golang in the backend, which I was not familiar with, and the companies usually have their own internal ML pipeline for developing and deploying models. So there's some onboarding time required to get used to this new infrastructure as well. A key aspect of moving away from academia to industry is that you need to start dealing with real world data. You're often used to training with clean curated data sets in controlled Jupyter environments, but once you start working, you need to train models with messy real world and often limited data. So this involves data having outliers, varying distributions between training and test set, and imbalanced data. So you need to make sure that the data is clean before you actually ingest it into the model. Another key mindset shift once you move from academia to industry is moving from the local model perspective, where you're very focused on just improving the accuracy of the model, to a more global perspective where you're thinking about the pipeline end to end. So, when you're dealing with production problems, you often need to prioritize product requirements, infrastructure constraints, latency bounds, and user experience over model performance. The model is generally a smaller component, and it's used to enhance the predictive power of an already existing pipeline. So you need to adhere to the system constraints first. So thinking about models by focusing more on deploying, maintaining, and scaling these models in and automating pipelines that enable the same is more important. Another key aspect of my transition was trying to translate theoretical ML algorithms to practical use cases for gaining more useful insights. So, an example of this is so Lyft conducts planning sessions before each quarter where we try to identify projects that we want to execute on in the upcoming quarter. This requires rough impact estimation to decide project prioritization. In one such planning session, there was a project in discussion to implement some tweaks to the rider pricing algorithm. But to understand the impact of it on rider conversion, we modeled a simple logistic regression algorithm to understand the exact coefficient of the change in rider price and its impact on conversion, which was a business metric. So, what does a day to day in the life of an MLE at Lyft or more broadly in a rideshare industry look like? So, it's not super different from what an MLE in any other industry would do, but on a day to day, I collaborate with product managers and data scientists to identify use cases and projects where algorithms can be leveraged to enhance the predictive power. I also work on writing advanced SQL and optimizing queries for efficient data processing. And then once I fetch the data, you also need to ensure data quality and integrity, since, as I mentioned, real world data can often be messy. So you need to perform data wrangling and cleaning techniques, do offline inspection before you actually create the set of features that you want to ingest into your model. Identifying and prototyping the right algorithm is also necessary, since it needs to be aligned with your problem type as well as the business use case and, of course, the system constraints. So, you need to spend some time in prototyping the right algorithm for your problem. And in the process, you also need to do hyperparameter optimization for optimal performance of your model. Evaluating the model using appropriate metrics, deploying and running A/B tests for new models to identify the impact on users. These are some of my other day-to-day tasks as well. Finally, a key task, I think, is to monitor metrics for model performance and build dashboards for observability, because even once you've trained and deployed the model to production, you want to ensure that it's working as expected over a long period of time. So, ensuring good observability, setting up retraining, these are some of the key aspects of an MLE's job. There are also obviously production issues and anomalies that creep up from time to time. So there's a good chunk of time spent troubleshooting that as well. We've also been conducting brown bag sessions and knowledge shares in our team. So that could range from latest ML research papers to new discoveries in marketplace optimization or just general project discussions and brainstorming. So, before I talk about the individual steps in an ML training pipeline, I want to focus on the fact that before you start any project and decide whether you want to leverage an AI or ML algorithm, it's necessary to look into things like, is your application very latency sensitive, and does the reliability of the application precede the accuracy? Because if you have a simple heuristic that can perform the same job with good enough accuracy for you, then you would probably want to rely on that rather than leveraging a complex ML algorithm. So, assuming that you have decided that you want to leverage machine learning for your problem, these are some of the steps in the training pipeline that are pretty common across all the companies that leverage ML for their problems. So the first is the data ingestion step, where you collect data from various sources. So to create a training set, it is imperative to first identify a superset of features that are relevant for the model to predict the target label. These features are not carefully curated and stored in a single database, as was the case in an academic setting, but often need to be ingested from multiple sources and offline data stores. So it's also helpful to think how these features would be fetched online, because if it's not possible to productionize these features and fetch for online inference, you probably would not want to waste time testing it in an offline setting as well. One of the solutions that Lyft has implemented is to create a centralized feature store. I've actually linked the blog that talks about this solution. It's a feature store which is deeply integrated with the company's data warehouses to support both training jobs as well as low latency online inference. So, this supports both batch features, which are scheduled airflow jobs that compute features at, say, 1 hour or 2 hour cadences, or event streaming features, which are more real time. So this supports reusability as well as scalability, because the same ML features can be used by multiple teams across Lyft. So once you've fetched your training data, it's necessary to understand the distribution of the data at hand. So exploratory data analysis is a common next step, where you assess the quality of the data, plot graphs to understand the distribution of the data and the correlation between columns. So once you've assessed the data, you would want to perform some data wrangling steps, like normalizing, cleaning the data by filling in missing values, removing outliers, etc. So this is the data wrangling, and then you create your relevant features for the first iteration, which is the feature engineering step. So this the first and second points are basically how you build your training set. One aspect here is to always split your data into training, test, and validation sets, because this is a common concept discussed in machine learning where you want to avoid overfitting. Time based splits are often preferred for rideshare marketplace models because data distributions change over time. So training generally happens over a month or 2 months worth of data, and then the evaluation is done on the subsequent month. Another key point to note is that the data splitting should happen prior to the data processing, pre-processing, and feature engineering steps. Because suppose you're filling in missing values using the columns mean, then you would not want any leakage from the test set into the training set. So these are just some of the points to avoid overfitting of the model later on. Once you have curated your training data, now it's the time to choose the appropriate ML algorithm that you want to train based on the problem type. So it could be the classification, regression, or image recognition. And this also depends on the data characteristics, whether you're using structured or unstructured data. Always tie the algorithm back to the infrastructure constraints, because you would not want an overtly complex algorithm if your system does not have the bandwidth to support it. So now's the fun part. You get to train your model offline. If you're using an off-the-shelf open source library as your model, then you would want to read the documentation carefully, because usually these libraries have several parameters that you can tweak to control the trade-off between model complexity and overfitting or underfitting. So the trade-off between complexity and accuracy but can be controlled by tweaking these parameters. And this step is also known as hyperparameter optimization. So a common technique is to implement cross-validation to optimize for this set of hyperparameters for improved performance on the test set. um, I've linked an interesting thread which talks about nested cross validation and why you should use it instead of just cross validation to determine the right set of hyperparameters for optimal model performance. Another thing to note is if you're comparing multiple models, always tune the hyperparameters to obtain the best set for each model before you compare amongst different models. Once you've trained the model offline, you can assess the model performance on an out of time test set using metrics specific to the problem's algorithms. So that could be accuracy, F1 score if you're using a classification algorithm, or a root mean square error metric for say, a regression algorithm. It's important to note that these evaluation metrics should be chosen depending on the business use case. So, if for your use case a false positive is more critical than a false negative, then you would want to focus on precision over recall. So once you've tested the model offline, now's the step to deploy the model. So you've tested the model. Now you need to write inference functions to load the model in an online setting, encode features from requests, and then invoke the actual model to generate responses. So the way to do this is to gently deploy the model locally or in cloud by creating a Docker file which defines all the runtime dependencies for the model and the serving script. Once you've deployed the model to production, it's imperative to set up observability dashboards and testing in production to ensure that the model is performing as expected and is accurate enough for practical use. So at Lyft, it's common practice to conduct A/B tests or run time split experiments to test the impact of these models against business objectives before deploying it to 100% of our users. Now that we've spoken about the training pipeline, I'm going to walk through some of the challenges that I've faced during implementation and solutions that I've identified for the same, either through online research or by just talking to peers and mentors who are more experienced. In the first step, that's the data processing step, a common challenge is processing data at such a large scale, both for offline training as well as for online inference. So, a solution that we've implemented at Lyft is to use the centralized feature store, which serves ML features for both offline training as well as online inference. And that helps some of the reusability and scalability aspect. This centralized feature store, since it also writes to offline tables for supporting offline training, we also circumvent the issue with disparity in data distributions that are observed between online inference versus offline training. One of the other solutions is to leverage distributed training frameworks like Spark or Dask for offline computing. You can easily find documentation around these frameworks, so definitely recommend that. The issue with data bias is also another common problem faced in production machine learning. So, this is a gradual shift in data distribution in a production environment seen over time, because when you perform offline training, that is usually over a fixed period of time in the past, but your model is continuously inferenced online over a long period of time. So it's very natural for the data distribution to shift, and that impacts model performance. A solution to this is to leverage data and feature validation checks. So, as the online feature requests come in, you have a feature or data validation check, and there's a tool called Great Expectations, which is a third party tool. And using that, you can easily leverage these checks to ensure that you can intervene and retrain the model as required. So the production data also represents the most recent relevant data distribution. So you would want to set up a dynamic data collection to store this data in offline tables, so you can leverage this for retraining later. Or you can also have scheduled cron job queries to ingest the data into the model for periodic retraining. An unexpected outcome of data bias is, of course, as I mentioned, performance bias, where the model performance degrades over time. This is commonly observed in dynamic rideshare environments, either due to data or concept drifts. So, data drift is when there is a change in distribution of the data over time. This was more recently observed during COVID 19, where over the period of 1 to 2 years, we observed a stark shift in commuting patterns. Or concept drifts, which involves a change in the relationship between your feature set and your target labels. This can happen due to a change in business objectives, for example. So, this can inject a negative feedback loop into training if the model outputs are used for training the model. So, you can imagine that there is a model which is predicting degraded outputs, and the same outputs are fed into the model for retraining, and that just keeps escalating the error rate of the model. So, one of the solutions to this is periodic automated retraining with recent production data to mitigate performance declines. Another common observability technique is to set up model performance monitoring in production to catch unforeseen issues, and just performing general regular audits of model health, and inspection of edge cases so that the issues do not escalate in production. One other challenge that I've always faced is that offline training generally results in an overly optimistic performance of the model. But once you deploy the model to production, the model performance is a little degraded. And that also happens due to a difference in data distribution between your training and production setup. And as I mentioned previously, the centralized feature store could be a good solution to circumvent this issue. Another solution is that before deploying the models fully into production, you could set up shadow execution for offline analysis. So this means that you allow the model to make predictions on production data, but you don't actually use that for decision making. You perform offline analysis and tests to make sure that the performance is as expected before you deploy it to production. Also, as I mentioned, running A B tests or experiments is a common way to catch these issues before you deploy the models all the way to production. In a rideshare industry, we have multiple objectives that we are trying to optimize for. So there's rider experience. We want an enhanced driver experience as well as company profit. So there are hierarchical decision making models that we leverage using constraint optimization techniques as solutions. Given the dynamic environment of rideshare with rapidly changing marketplace conditions that affect real time demand and supply distributions, sometimes just automated retraining is not enough because even if your model retrains as frequently as a day, even if it trains on a daily basis, there's still 1 day's lag before the model can be trained on the most up to date data and then update its internal weights to predict the correct outputs. So sometimes there's also a need for continuous online model learning, where this is also known as transfer learning, where the production model is continuously updated using data available on the fly, using event streaming. So, this of course needs solutions for scalability because it's often heavy and expensive for the model to train so many times in the day using data available on the fly. But if the application is very critical in the sense that it demands most accurate predictions, then this is a solution that you can look into. Another option is also to implement an ensemble architecture where you have the production model that is retrained at some daily or weekly cadence, but then you have a model bias layer on top of it, which tries to capture the difference between the between the production model outputs and the factual outputs. So the bias layer could be like a more lightweight model, which is trained in real time, say every 15-20 minutes, on data available on the fly. And its job is to basically try to predict the difference between production model outputs and the factual data. Scalability is a very common challenge across companies working with ML systems, because these systems need to process data and run inference on a large scale with sub-second latency. So generally, every company implements a cloud-based infrastructure for flexible scaling, and uses automated ML pipelines for efficient model deployment and retraining. As I mentioned before, it's very important to not over invest in model accuracy, because that can often be costly. So always tie your model to the product constraints as well as latency and infrastructure constraints prior to starting the project, because that often limits the available model design choices. So, before we end the presentation, I wanted to take some time to talk about the impact of the recent generative AI buzz on the rideshare industry. So, we've been looking into leveraging LLMs for various applications across rideshare, but some of the common ones I've listed here. So, the first is to use LLMs to streamline the rideshare app experience by using conversational booking systems where the riders can actually just use speech to request rides and manage their trips. So this can be super efficient and just reduce the time that the riders spent in actually going through the entire process of requesting a ride. An interesting use case is also to use real time language translation for global travelers who are using the app. We've also been looking into leveraging LLMs to mitigate common user concerns, because we can provide enhanced customer support through AI generated personalized responses, and reduce the manual intervention required to resolve these queries. One of the recent use cases that we have actually deployed in production is to use LLMs with few shot prompting to prevent phishing attacks. So, fraudulent driver account takeovers are very common across rideshare, where there are fraudulent messages which are sent to drivers, and they try to obtain driver details to hack into their accounts. So we basically label these sequence of messages as phishing or non-phishing through LLMs, and then we're able to prevent a lot of these scenarios. Improving driver assistance and training is another use case of the LLM, where we're looking into generating AI content for training content for drivers and provide real-time driving tips and suggestions, because it's a very nice solution to implement text-to-speech support for hands-free interaction with the drivers, since it's much safer as well. Also, drivers generally use drive on Lyft or Uber as part time employees, since they usually have a main gig and then they're driving on the side. So we would want to streamline their experience using the app by customizing driver scheduling. So this would involve generating personalized driving schedules using driver inputs and availability. We've also been looking into leveraging LLMs for summarization and sentiment analysis of rider and driver feedback for gaining insights and reducing manual analysis time. We've also actually implemented integrated LLMs with internal productivity tools like GitHub and Slack, and Jira as well, because it can actually reduce the time taken to do a lot of manual tasks like creating simple tickets or PRs on GitHub. So that has significantly improved the company's productivity as well. So, this brings me to the end of my presentation. Thank you so much, and feel free to reach out to me on LinkedIn or via email if you have any queries.